This week, we'll give a brief introduction to the concept of database development. As part of your reading this week, you're reading about the relational model. We're going to go in a little more depth with that next week. Here, we're going to talk a little bit about some of the concepts that are involved when you create a database, more specifically, when you undertake a database development project. So let's begin. What's in a database? Well, in the textbook chapter you're reading this week, you'll learn all about this idea of tables. But at an abstract level, we're concerned with really two things: entities and relationships. Ultimately, this is the type of data that is going to persist within a database. Entities you can think of as the nouns in a business case. These are the objects you wish to store in your database. The examples given here are meant to illustrate that. Things like students, classes, suppliers, and parts. It's relationships that link the entities we care about together and tells us something about how those entities interact. This interaction is often called a relationship. In the relational model, or more specifically in a relational database, we often think of entities within a table. A table is the logical unit of storage in a relational database. A table, if you remember from perhaps prior experience with Microsoft Excel or Microsoft Access, is nothing more than a two-dimensional grid with rows and with columns. In database speak, a table contains many records. Each row represents one record in the table, and this row represents information about a single entity. These rows are broken up into columns, and it's these columns which are the properties, or sometimes called the fields, of the individual record. In other words, the individual pieces of data about a specific record. In a relational database, some columns are considered what we call keys. These are one or more fields which tend to yield a unique row. We use keys for such thing as searching and matching when we're looking for specific records. It's important to remember that, like any large IT project, databases need to be developed. There are many steps involved, along with usually many people involved, who are all working in the hopes of creating something that can be used on a large scale by a given organization. Database development includes three basic pieces: constructing what we call schemas, which are descriptions of data, for three levels of the database system, creating end-user applications, and installing and configuring a DBMS so that response time is fast, storage is efficient, and everyone's happy. Here's a graphical depiction of what we call three-level architecture. This is a database concept, where the database is separated into three distinct levels, each of which requires development and design. At the most basic level is the physical level, which is the actual database, which are often represented schematically with a cylinder, as we see here in the diagram. Above that, you have the conceptual level, which is generally thought of as being the DBMS. This is where we see the data as tables, whereas in reality they may be stored on the physical disk or physical storage device as something very different, such as ones and zeros. At the conceptual level, we see data as tables, and we use software to help us interact with the physical database. One level above that is the external level. This is how the rest of the world sees it. People like programmers, end users who may be using the database through a web form or a web page, or any number of data entry mechanisms, and administrators who may be generating reports about monthly sales or trends in the market. Here's a diagram of how development used to proceed in the past. Now, this is considered to be a fairly archaic way in which systems are designed, but believe it or not, there are still many adherents to this particular methodology. In the past, we would begin with a preliminary investigation, and from that we would develop a problem statement and maybe do a feasibility study to see if the database project was feasible to do. From there, we would work our way into systems analysis, And from that, we would produce a set of system requirements. We would then roll into design, producing a set of design specifications, and then we would actually try and implement that design and produce an operational system. And if all went well, the system went live, and we entered the maintenance phase, where we would fix bugs, add new features, and adapt over time as the individual project was being used. This is a fairly linear model. We call it the waterfall model because of the staggered approach you see here in the diagram, and it's largely fallen out of favor in terms of its methodology. This is especially important now when we really have a world that is interconnected by technology and more people than ever reliant upon that technology. So here's a model that's a little more modern. We of course still need to gather requirements. In other words, what are we being asked to do? We then design a solution, we implement it, we test it out, and we gather feedback. But what separates us from the waterfall model is the repetition. This is a cycle, a continuously repeating cycle, where systems are built a piece at a time rather than one monolithic project where we produce one big deliverable at the end. With this, we refine our project as we go, producing small pieces here and there, and we fix bugs early and fix design issues early rather than do it all at the end. The ultimate goal of database development is ultimately to produce an operational database, something that's useful to an organization and it serves the data needs of an organization. Like any piece of technology, it has to be useful and provide some sort of economic benefit for an organization to adopt it. So what makes it useful? Well, one thing that a database can do within an organization is to provide a common vocabulary. Often you take large amounts of data from different parts of the organization and bring them together under one umbrella, under one database. In doing so, you have to make decisions about what you call certain things. When you have a large dispersed organization, sometimes the different wording is used to describe the same basic thing. This forces the organization to look at how it's naming things, how it's referring to different elements of its business, and to come up with some uniform set of words and vocabulary. More importantly than that, perhaps, is that a database helps to define the meaning of data. What does data mean? Well, in business speak, we talk about business rules. These are facts about business processes that need to be enforced within a database. As a simple example, consider Penn State. It stores information about you as students in its large database. An example of a business rule would be the fact that your birth date has to be something reasonable. In other words, your birth date can't be 7/4/1776. That just wouldn't make sense. We can enforce business rules at the database level, at the conceptual level, by implementing what are called integrity constraints. Integrity constraints are just that, constraints, things that enforce or hold down any attempts to do something quote-unquote bad with your data. It's kind of like a check. Before data goes in, these constraints check to make sure that the data is valid for that context. Sometimes these constraints are very strict, and sometimes they're more flexible, depending on how they're implemented. It's through these integrity constraints that the database ensures valid data. Now, this is very important because for many organizations, data is the most important business asset and is a critical tool in making decisions. For business decisions, poor data truly does equal poor decisions. That said, database development can be an expensive and time-consuming process, so it's not undertaken lightly. This is especially true with the more data that an organization has. For example, Walmart generates a huge amount of data every day. Its database systems are meant to be airtight, so to speak, and changes to those systems do not happen on a dime. Much thought, much checking, and much careful design work goes into those changes. Data quality is an important aspect of database development. You want good data so you can make good decisions. And here are some dimensions of data quality that are considered. Things like completeness, lack of ambiguity, correctness, timeliness, reliability, and consistency. All of these dimensions of data quality are especially important to ensure that the data that we store in our database actually is useful and meaningful and valid for a given organization. There are 4 stages of database development we're going to talk about here. First, conceptual data modeling. That's really where we're going to begin more or less in this course. This is where we do some design work at a sort of an abstract level. We gather some requirements from our quote-unquote clients, and we produce a series of entity relationship or ER diagrams. What this does is produce what's called a conceptual schema. This conceptual schema describes the things that we care about in our database. If we were doing application type work at the external level, we would also produce an external schema using ER diagrams. For now, especially early on in the course, we're going to focus on this idea of the conceptual schema. Entity relationship diagramming is a standard business tool to produce a visual indicator of what it is we want to store in the database and how those things or entities are related. It is not meant to be specific to any particular database, whether it be DB2, Oracle, SQL Server. It is meant to be an implementation independent design. Logical database design is where we start to take our design work from the conceptual data modeling and produce something tangible inside a commercial DBMS using SQL. This is where we take our design, we use SQL to create actual tables in a relational database, as well as the relationships between those tables. As part of this work, we undertake a process called normalization. Remember in the past we talked about redundancy. We said it was a bad thing. Well, normalization is sort of a post-processing design step that's really undertaken to remove redundancies that may have crept through in the conceptual data modeling phase. You'll read more about this in your textbook chapter this week, and we'll focus on it a bit more in the future. The last 2 stages are distributed database design. This is especially important if you have a database that is not just isolated within one building or one organization, which is often the case. You make choices about the location of data and processes to improve performance. Obviously, you want your database to have quick response time, to be constantly available 24/7, but you also want to have control mechanisms in place to ensure security and to ensure that bad data does not enter your database. Finally, physical database design is where you start talking about things like servers and memory and hard drive storage. But beyond that, you also talk about some DBMS tools that we'll mention later in the course, such as indexes and other details which can be used to make databases even more efficient. Finally, we want to talk a little bit about data migration. Anytime you undergo a database project, often you're taking data from one place and putting it somewhere else. And by place, I mean from one format into another format. Maybe taking data from a CSV file to an SQL database, that type of thing. This concept is known as data migration, and it is not done lightly. You need some element of quality control when you do that migration to ensure that the data going in is both valid and of good quality. Depending on the source of the original data, it may have holes, or it may have things which don't comply with the business rules that you came up with during your design work. The process of migrating data and perhaps even fixing the data as it goes into its new location is called scrubbing or cleaning the data. And this is an art form in many ways, because data migration is not always done with off-the-shelf tools. Sometimes you have to write custom code to move data from one point to another. With the UAdams project that we talked about last week, this was the case. We had to write custom code to move the data from one format to another in multiple instances. In the end, it's important to remember something that you may have heard of in Comp Sci 101. Remember that garbage in equals garbage out. So you have to make sure that the data you have going in is quality data. Otherwise, it will lead to bad decisions when you go to analyze your new database.